This second part on PLS is about validation, and as for PCA, that means determining the number of components and checking for outliers. Many parts of this will be exactly the same as for PCA, so for these parts we won't go into detail, as you have already gone through, for example, using score plots for detecting outliers in PCA. Before we talk about the specific validation, it's also important to note that there are different levels of validation that you can perform. For example, we have statistical validation, where we, for example, build confidence intervals. We seldom use that in chemometrics, for one thing because we simply don't have the right equations to use. Little is known about the statistical properties of different chemometric models. But there are also some philosophical reasons not for using that. For example, we do not want to trust entirely statistically based measures. We want to show in reality that the model we build will work, for example, on new samples. And for that we have what we could call empirical validation, where we look at predictions, for example, from cross-validation, and see how is the model actually performing on new data. And then we have another kind of empirical validation, which we could call comparing the model to external information, or which we sometimes call interview validation. That is very seldom described in the literature, but it's one of the most important parts of validation. Making sure that your model is explaining what you expect to be seeing in the data, or confronting experts with what the model is showing. Such validation can be crucial for building correct models, but it's difficult to put into numbers and figures. In this part we will mainly talk about the middle kind of validation, cross-validation and test set validation. The cross-validation is similar to the cross-validation that we talked about for PCA, only in the PLS situation we are interested in predictions of Y. We are not primarily interested in how well we describe X, only to the extent that it helps us predicting Y. But the basic problem is essentially the same. The more components that we use, the better we will fit the actual data. So if we take all the possible components, we can in most situations describe Y as well as we please, as shown in the lower plot by analogy in curve fitting, where if we take a sufficiently high degree polynomial, we are able to fit a line through all the points, but we can see that it's not describing the structure in the data very well, and we do not expect that this line will be adequate for new samples added in between. We need a model with the right number of components, enough so that it explains all the systematic variation in the data, so that it explains what can be explained, but not more than that, because then we are modeling the specific noise in the data that we have, and we are not interested in that. That will not help us predict new samples. And therefore what we do is that we leave out samples. We leave out, for example, one sample. We fit a model, a PLS model, and with that model we predict the left out sample and get residuals. So we see how well is the sample predicted when it was not in the model. We repeat that so that all samples are left out once, and then we get a total error. But instead of fitted residuals, we now have cross-validated residuals, and that gives us residual validation variance, or the root mean square error of cross-validation. And we repeat that for many numbers of components, and the number of components that will give us a minimum error, that's the model to choose. When we have performed the cross-validation, we can get a plot as the one shown here. Here we see the root mean square error of cross-validation and the root mean square error of calibration as a function of the number of components. The blue line, the calibration, is showing that the more components we use, the better we predict the actual samples. But for the cross-validated samples, the samples that are left out, there's a minimum in the curve. So that will be the optimal number of components to use. For real applications, it's not always as simple as shown here. Sometimes the curve is just sort of flattening out instead of having a clear minimum, but then you have to use additional diagnostics. Look into the score plots and see if that extra component could be real, reflecting something you know, in order to assess whether to include it. Or maybe you prefer not to include components that only add a fractional additional explanation if not needed. Here's an example of how it could look in Unscrambler. The data are ultrasound images of features extracted from ultrasound images of pigs, and from those features we would like to predict the fat thickness. And we can see on the left plot that after one component nothing much is gained by adding more components. The blue bars show us the calibrated variance, and the purple one the validated, the cross-validated variance. In the right plot we show the predictions we're using one component, and you can see that it's one component in the lower part where it's shown in parentheses, comma 1 means using one component. We see both the validated and the calibrated samples in the plot, but we can remove the calibrated samples if we want to have a clearer picture. Instead of using cross-validation, we might use test set validation. The difference is not that pronounced. What we do is that instead of leaving out samples one at a time or some at a time, we divide the dataset into two, a calibration set and a test set. So we build the model using the calibration data, and we evaluate only on the test samples how well we predict. And then we choose, as in cross-validation, the minimum as the correct number of components. We call this a dependent test set, because the model uses it to decide what the model should be, how many components to use. When we want to assess how well the model really predicts, then we have to test that on a new data set. That is what we call an independent test set. So not the one we just talked about, but another test set that was not used for deciding how many components to use. So that's a virgin data set. From that we can get the best estimate of how well the model predicts. But sometimes we cannot afford splitting our data into so many different sets, and instead we will, for example, use cross-validation in order to use all the samples as efficiently as possible, and we will perhaps not have a huge independent test set, but we will just verify the model on a few samples in order to make sure that it really works. But the optimal thing to do would be to have a completely independent test set reflecting all the types of variation we expect in the future. From that we would be able to get a very good estimate of the error, how well the model would predict in the future.